this section, we're going to look at where do syndepositional saline clays or authigenic clays form. We saw in the previous section how in the perennial lake setting we had the neoformation of clay minerals, magnesium silicates such as kerolite and stevensite. We're now going to expand that discussion to look at a variety of saline, pan and capillary zone hydrologies where various magnesium silicate clays, authigenic clays, are formed. Let's focus in on the hydrologies and the hydrogeochemistries associated with that formation. In our discussion of clay minerals, we put it in a broad framework of depositional associations. We saw how the kerolite, smectite mixed layers and the magnesium smectites, the stevensite, sapphonite clays, tend to accumulate in what were the open lake, saline lake, sometimes ephemeral, more often perennial associations such as Lake Yao, where we saw these accumulations of these magnesium silicate minerals as neoformed primary precipitates. We're going to move to the margins now and look at the associations with palygorskite, sometimes known as attapulgite, where it's mixed with magnesium smectitic clays. We'll also have a look at sepiolite, and we'll see how there is a distinction between the brackish settings associated with sepiolite and the more ephemeral playa lake associations in the mudflat margins, and even in the alluvial fans associated with the formation of authigenic palygorskite. Before we get into the details, let's just define in general what is an authigenic clay. Well, we know that in saline depositional systems we have fluctuations of the region of the saline pan. So in this look at Lake Eyre, where we have north to the left hand of the image, we can see the effects of saline pan fluctuation. Those white and pink areas in the southern areas are areas of salt crust covering the clay floors. To the north, we can see those channels flowing down into what are the ephemeral surface water-covered saline flats, where we have fluctuating water tables moving up and down, sometimes flooded and water-covered, other times desiccated and severely exposed regions of these mudflats. Within that framework, because of this fluctuating long-term brine flushing associated with the transitions between phreatic to capillary to vadose hydrological cycling, we have authigenic clays, often forming both as neoformed clays and as replacement clays. Authigenic clays are those clays formed or generated in situ. That encompasses a whole range of clay minerals that are not detrital, that are not transported into the basin. Rather, they crystallize locally at or near the spot where they're now found. They came into existence at roughly the same time of that early eogenesis, that early diagenetic association, or they can be subsequent to the depositional association of that clay, and then they see alteration overprints on that clay. We noted in our mineralogical discussion that many of those replacement clays inherit the elevated levels of alumina brought in by that original smectitic or oolitic or chloritic mineralogy in those detrital clays. What is clay orthogenesis? Well, it's the formation of clays by direct precipitation from a solution, and we call this neoformation. We focused in on neoformed clays in the perennial lake system. In the previous section, we looked at stevensite and kerolite. We're now going to look at neoformation within the framework of pore fluids on the lake margins. We'll also look at clays that are neoformed by transformation from a precursor mineral. Precipitation from a solution, it can be a pore solution or it can be a freestanding lake water, where there's a new mineral forming, a new magnesium silicate forming with no prior mineral. Or we can have the transformation of a precursor detrital mineral, replacement if you like. We sometimes call this neoformation by addition through precipitation on a pre-existing natural surface or transformation and reaction on pre-existing mineral surfaces. So within this discussion of authigenic clays, we can have sedimentary evaporative authigenic clays, or we can have diagenetic, which is post-depositional replacement in intrasediment situations, pore fluid situations. We sometimes call this type of authigenic clay the transformative clay. Both are types of authigenic clays within a background of what is detrital clay deposition, where we have clays coming out of the weathering profiles in the lake margin and being carried into the sump. So we can have detrital clays with no subsequent saline clay orthogenesis, or we can have those clays being altered. We saw in that previous section how large levels of detrital input of clays tends to minimize the level of orthogenesis. Low detrital input is a factor that favors the formation of saline orthogenic clays. Orthogenic clays develop typically in marginal and brine-saturated areas in lacustrine sumps in the lowlands, where we see low rates of detrital clay input. These could be regions like interdural depressions, peripheral mudflats and sandflats, or regions with ephemeral shallow brines. Across the board, these are regions with low detrital input, so we see the transformation of a precursor clay being much more effective. We may have episodic water coverage, or surface inflow, which gives us also a supply of detrital clay into that low detrital depositional association. We can see ephemeral surface waters, and we'll also see ongoing recharge from saline groundwaters being recharged through that clay association by the process of capillary rise. We say that these slushy margins of these saline lake systems encourage orthogenesis. So there's a slushy margin on the ledge of Eyre in South Australia. It's subject to periodic flooding and then desiccation, giving us that slushy, capillary-rich hydrological association. Clay orthogenesis in many modern saline sumps is driven by this periodic slushy pedogenesis. It forms in the soil profile, not just in the perennial lake profile. These slushy pedogenic profiles characterize the warm margin with still isolated saline areas, typically in mudflats where the sedimentation rates are relatively low and subaerial exposure dominates on the sedimentation surface. Because of that episodic wet-dry cycle that we see in these ephemeral saline pan or saline mudflats, we often see desiccation cracks, and those desiccation cracks act as preferential inflow zones for the types of fluids where we have saline orthogenesis taking place. Those fluids can be coming in from above during evaporative concentration when they're water covered, or they'd be coming from below during times of subaerial exposure and capillary rise. In both of those episodic wet-dry cycles, we'll see our neoformed clays as a byproduct of what are quite complex interactions between both sodic and magnesium-rich interstitial brines with the detrital silicates. So this type of slushy margin, this saline pan hydrology, accounts for the formation of quite widespread lake margin palygorskite and also sepiolite associations. Because they're in that ephemeral saline pan capillary evaporation margin, we often see a co-association with pedogenic calcaretes or dolocrites or silcates, and also in the more saline areas, the formation of gypsiferous profiles within that pedogenic lacustrine margin. Now, not all of this alteration has to take place in a semi-arid to arid environment. This plot by De Campo from 2015 shows us a range of environments where we see that orthogenic enrichment in octahedral magnesium plotted against octahedral alumina from the original detrital clay, and we can see how in those zones where we have this transfer of magnesium-rich solutions, quite often in alkaline waters, we see that increased level of magnesium in those orthogenically influenced clays. So in Ngorongoro crater, in Kenya, which is in a warm, temperate situation climatically with a dry winter and a warm summer. So we're not looking at very arid here. We see the difference between the uplands versus the lowlands where we see these alkaline pore fluids and perennial waters interacting with those clays. We can also see it in the Pantanal wetlands in Brazil, which are actually a tropical climatic setting with a dry winter to give us the evaporative input into those settings. As we also see in Amboseli in Kenya, same climatic association, we see that enrichment in the levels of magnesium in the smectitic clays, in what are not really arid to semi-arid environments. And we go down into environments where we do see them in a more semi-arid setting, in Great Salt Lake, where we're looking at what is a desert steppe in a cool climatic setting, or in Lake Chad, where we're looking at a desert setting in an arid cool setting. We see that magnesium enrichment. The commonality of all these smectitic clays showing magnesium enrichment in these settings is that the surface or the pore waters are alkaline. The aqueous silica activity is quite high. There's typically elevated levels of magnesium in the pore fluids or in the surface waters. And they're also in areas where levels of detrital input are relatively low. Those precursor clays, those detrital clays, give us the availability of both alumina and iron. Their alteration will likely give us a more magnesium-rich smectitic association, could come from illite, could come from a less magnesium smectite. Whereas when we get into the more arid areas, as we looked at in the previous section, we tend to see the more magnesium silicates forming neoformed varieties in what are saline alkaline environments, quite often perennial saline alkaline environments, where we don't have a detrital substrate, so we don't see residual alumina in the clay mineralogy. These are pure magnesium silicates. We saw the effect of that in diagenesis, leading to the creation not of another form of clay, but of dolomite or chert, as those magnesium silicates alter in those later stages of magnesium enrichment. Let's have a look at more detail at Lake Ngorongoro in Kenya, which is an internally drained caldera collapse crater. It's created a hydrologically closed basin. The basin itself, the Ngorongoro crater, is perhaps the world's largest subsidence crater, and it's the 5th largest caldera in the world. It's now an inactive, unbroken, unflooded caldera with a perennial alkaline lake, Lake Makat, in the centre. There's a hippopotamus population living quite happily in these lake waters. The TDS in these Ngorongoro waters is ranging from 130 to nearly 10,000 milligrams per litre. Remember that seawater has a salinity of 35,000 milligrams per litre, so we're a third of the salinity of seawater here. The freshest water are found in inflowing streams around the margins. They're fed by freshwater springs near the margins of the volcanic crater. It's actually got a perennial hippo bath in those springs. The most dilute waters show calcium and magnesium dominating the cations, but as the waters become evaporatively concentrated in the various clay-rich mudflats around the margins, we tend to see sodium and potassium coming to dominate. It's located in a region where to the north and the south, to the north we have Lake Natron, to the south we have Lake Eyasi and Lake Manyara, much more saline systems. But this is a less saline system in what is a tropical climatic setting with a dry winter, giving us that evaporative phase. Within that system, we see wind action in the exposed marginal saline mudflats and sandflats, reworking what is a sodium carbonate dust. We can see it in action here, where from the lake flat, we are blowing this material around. It's blowing into the wetlands, permanent water-covered areas of the lake, and giving us an additional source of cations dominated by sodium along with bicarbonate. Now, if we look then at the chemistry of these waters as we go from the freshwater intakes into the lake mudflats where the saline concentration is occurring, we can see a progressive loss of the alkaline earths to mineral precipitation. It's taken out by calcite, which is abundant on the land surface. Some people call it a calcrete, but there were no magnesium carbonate minerals in that phase. The magnesium is staying in the solution, but that brine is developing elevated levels of sodium and magnesium on top of those incoming detrital materials, typically a dioctahedral smectite, which is reactive. The various clay minerals across the basin floor also include a variety of magnesium smectites. The authigenic phase here is not as obvious as it is in some other lakes, but what's interesting here is if you look at the lake chemistry, the mudflats are smectitic, and the pore fluids are supersaturated with respect to authigenic silicates. We see increasing levels of carbon dioxide in these pore fluids from organic decay, from the rotting of cyanobacterial mats and associations. That elevated level of CO2 has an interesting effect on the sepiolite and the kerolite saturation. Now, these lake waters are quite alkaline. They have alkalinities in excess of 7, but they are less than 9. And so what we tend to see here is an undersaturated association for both of our magnesium mineral phases, kerolite and sepiolite, related to elevated levels of carbon dioxide. Now, that observation that the CO2 levels are driving the dissolution of those magnesium silicates, not the precipitation of those magnesium silicates, has interesting implications for ancient saline muds, where we see a drop in the magnesium silicate content in what would otherwise be a prime candidate for magnesium silicate precipitation. And so those drops that we see in ancient environments, and this is an argument made by De Campo back in 2005 and in 2015, that those drops in the levels of the magnesium silicates within the lake stratigraphy may not be a depositional association in the sense of inappropriate chemistries in terms of magnesium levels, but may be indicative of biogenic CO2 enrichment driving dissolution of magnesium silicates. There's another factor to put into our association with alkaline waters. We also have to consider levels of CO2, dissolved CO2, in those pore fluids, which act to the detriment of the formation of magnesium. magnesium silicates. Okay, let's step back and look at what's happening in the lake margin where palygorskite, attapulgite, if you like, are forming. We're seeing the transformation of a pre-existing detrital mineral, the aluminum-bearing clays, into a palygorskite saponite association. This is sometimes called geochemical pathway 1. The formation of stevensite and kerolite from perennial permanent waters is called pathway 2. In pathway 1, in the margins of our alluvial mudflat system, in the alluvial fan system, in the updip areas, we can have palygorskite forming in zones which are very close to the weathered parent rocks that are supplying the magnesium and the silicate and the alumina-rich clay. They're forming in the weathering profile around the uplands margin where we have the appropriate chemistry and the appropriate semi-arid situation. In that alluvial margin situation, we have the right pH, the right magnesium to silica ratio, as well as somewhat elevated salinities in that semi-arid margin to form a syngenetic association of palygorskite or attapulgite, where we have a magnesium smectite weathered marginal parent rock coming off that system. There's another situation within geochemical pathway 1 where the palygorskite also forms, and that is where we have in the actual lake edge mudflats periods of long subaerial exposure in what is the more distal alluvial fan facies closer in to the lake water body, where we favour the formation of pedogenic palygorskite, overprinting as a authigenic clay the original inherited aluminous clay. That same process is also associated with the production of calcite, calcrete soils, and local pedogenic gypsum. So these are replacive processes where we see calcretes associated with the formation of palygorskite within what is a alumina-smectitic illite host as a transformative replacement process. Further out into the lake, we see saponite in preference to palygorskite. Here we have a situation in geochemical pathway 1 for the formation of magnesium silicates, where we have the appropriate salinity, pH, and elevated magnesium to silica ratio, giving us the syngenetic formation of palygorskite and sepiolite around the lake margin and kerolite or stevensite within the lake waters in the geochemical pathway 2 areas in what are highly alkaline, magnesium-rich pore fluids and lake waters. Quite often these environments are related to that flood desiccation cycle we mentioned earlier. We drive this early diagenetic transformation of magnesium clays and the formation of intrasedimentary palygorskite by these fluctuating water chemistries. In areas closer into the lake, in particular the mudflats where the waters are more alkaline, rather than palygorskite, we transform those aluminous smectites into saponite, which is favoured over palygorskite, closer into the mudflat margins, with palygorskites forming a more distal facies in these geochemical type 1 pathways. So let's have a look at the characteristics of these pedogenic capillary palygorskites. We've got a typical palygorskite profile. This is from a Mexican iridosoil in what is a semi-arid setting, where we see a transition from an arid regolith into a slightly more differentiated soil under vegetation, where we have a higher level of moisture fluctuation. As we go down through the profile, we have a surface horizon underlain by a subangular polyhedral or PED structure in the AB horizon. We pass down then into a more dominantly polyhedral to prismatic structure where we see smectite along with some palygorskite in horizon B. Below that we have the lutite or the fresh parent rock. So this B horizon is a result of transformation of the original smectitic clays into a palygorskite association. It's not a process of lixivation. It's not a process of infiltration of clays from the upper horizons. Rather, the lack of cutans in that B horizon is showing us that palygorskite is forming diagenetically in situ. And that's being favoured by the elevated magnesium and alkalinity levels in that B horizon within this iridosoil in this semi-arid lake margin in Mexico. In the lower left, we have a phase diagram, which is a calculated system at 25 degrees and 1 atmosphere pressure in the silica, magnesium, alumina, water phase diagram, showing us how pedogenic palygorskite is being favoured by more elevated magnesium levels. This type of palygorskite is indicated by a lack of cutans in the pedogenic structure and by enrichment in the pore waters of magnesium. Palygorskite in these margins are found either in the alluvial fan, where we're weathering the pairing material and altering with the appropriate water chemistry, or further out in the mudflats. So it's found in what are arid to subarid climates with neutral to alkaline saline pore fluids, where we also see an association with carbonate and gypsum precipitation. Indicative of that neoformed origin of the palygorskite is forming in fractures in an already pre-existing matrix. Sometimes we see it replacing a pre-existing clay, which is typically the alumina-containing clay, and it's also quite smectic, giving us that favorability for palygorskite. If we look at the general levels of pedogenic palygorskite, we tend to see more palygorskite being developed in a gypsiferous soil compared to a calcareous soil because the formation of the gypsum indicating a higher magnesium to calcium ratio. There are other factors for palygorskite formation: alkaline pH along with high silica solubility.